Hi everyone, we're going to talk briefly about reduction. You've learned in the past that aldehydes and ketones can be reduced to alcohols using a hydride reagent such as lithium aluminum hydride, LaH, or sodium borohydride followed by water workup. So in this situation, we're talking about carboxylic acids and their derivatives, which could have halogens or ester groups, carboxylic acid or anhydride. So if we had some other kind of group here, like an OH or a Cl or an OR group, those can also be reduced. And usually I think of them the same way as I think about aldehydes and ketones, which is that I think of it as a hydrogen ion, even though that's not the case. Technically, these aluminum hydride and borohydride reagents have the hydrogens attached to the boron and aluminum, putting a negative charge on the aluminum or boron. And that gives the hydrogens then nucleophilic character as that negative charge sort of spreads out. So then this will want to attack the carbonyl. But instead of drawing that all out, I sort of do a shortcut, which is to think of it as hydride ion, which it's not really. But it works for me, and I'm okay with that if you guys do that as well. So I just think of it as coming up, attacking, and then in the next step, it will come down. And if Y is a good leaving group, like here or here or here, then this will come off. And then we'll get an aldehyde as an intermediate, which is also susceptible for attack by a second hydride. So we'd assume that there's excess, and we would come in again, and then we would get our alcohol. So that's sort of how I think about many of these reductions. Now, sometimes it's more complicated than that, especially for amides and for carboxylic acids, especially when there's a hydrogen to be considered. So if we have a hydrogen here, then the hydride would rather attack that hydrogen first. And I think we've talked about this before. For carboxylic acids, though, you will still get this alcohol, okay? But for amides, when you go through the reaction, you actually end up getting rid of the carbonyl group. So in that kind of situation, you might want to still think about this as a hydride. But just like with the carboxylic acid derivative, this oxygen will make a complex with the aluminum and the H3 that's left over. And then that enables one of these H's to come back in again. And this will eventually get lost. So it's a bit of a more complex mechanism with many more steps. But ultimately, that's how we lose that oxygen, it's a complex with the aluminum at some point. So that might be sort of hard to remember because that doesn't follow the pattern. Okay, so the pattern is when you have a good leaving group, you'll still be able to get the alcohol because you're going to keep holding on to this carbonyl oxygen right here. And aldehydes and ketones, of course, we also held on to that carbonyl oxygen. But for things like amides, it's a little more complicated. We see that oxygen is no longer present, and that's because of this kind of mechanism here. So just be aware of that discrepancy in the pattern. Another main point on this is I want you to see when you have something that's more strongly oxidized, like notice the amide, we really need the hydrogen to hit this hard to get rid of this oxygen. So I have to use lithium aluminum hydride for amides. I also have to use a lithium aluminum hydride when I have things like carboxylic acids and esters, which need a little bit more oomph from the reducing agent. They need a little bit more reactivity from the reducing agent because they're already pretty oxidized. Now these acid halides, aldehyde, and acid anhydrides, they're pretty reactive already. Aldehydes are very sensitive to getting oxidized to carboxylic acids, so they don't need something as strong as LaH. You can use NaBH4. Acid halides, we learned, are the most reactive on the ladder, so they are fine to react with hydride willingly. So they can do so with something weaker like sodium borohydride. Same with acid anhydrides. They're reactive enough that they can react with the more mild NaBH4. So take a look here. Some reagents need LaH. They are the carboxylic acids, esters, and amides. The rest, ketones, aldehydes, acid halides, and acid anhydrides can react with just NaBH4. Okay, and if you're not sure, you might as well just use LAH then, but just be aware sometimes NABH4 is used. As a chemist, I'd rather use NABH4 myself too. All right, propose an efficient synthesis for each of these reactions. So here I have a carboxylic acid, and I want to get to this cyclic acetal. I know that this comes from a carbonyl group, so just sort of stepping back, I know that this is what I came from. And then is there a way to go from this carboxylic acid to this group? Let's see, I know that if I had an aldehyde here, maybe I could do a Grignard reaction and then oxidize it to this ketone. So I know I'm sort of thinking about this, okay? And then at this point, if I had maybe an alcohol that I could oxidize to an aldehyde, there we go. Okay, something like that. And so maybe I can take this over to here and turn it into this, turn it into that, and then reverse these arrows, now working forwards, okay? So that's sort of what I'm thinking. So how do we do that? We have to reduce a carboxylic acid to a primary alcohol, and that's actually something we did up here. So when Y is a carboxylic acid, an OH group, this is a carboxylic acid, we do need to hit it with the harder LAH, okay, because it doesn't have the asterisk, so it can't just react with NABH4. So I'm going to use LAH, and I want to use excess. Oops, I put LAX. I'm thinking about visiting my dad in LA. All right, then we want to acid workup in dilute acid for getting this protonated. I want to oxidize this using PCC. Then I want to, remember, I just want the aldehyde, not the carboxylic acid, so I have to use PCC there. Then I'm going to do a Grignard addition. So I need an ethyl magnesium bromide. I'm going to then have this be an alcohol group, so I need to oxidize this to a ketone. So I can use Jones reagent, or, you can write it out. Jones reagent, technically it's CrO3, or you can use sodium dichromate in acid, okay? Then after we oxidize this, or you can use KMNO4, okay? After we oxidize this, I'm going to make my cyclic acetal using this reaction of ethylene glycol and catalytic acid. All right, that is a bit long, isn't it? But I hope you saw sort of working it forward and working it back. So the key for me was knowing this step right here. From a carbonyl, I go to this. And then also going forward, I know from carboxylic acid, I can make an alcohol. So you can sort of step it backwards, forwards, until you come up with the missing link, try to link it up. Now for the rest of these, it turns out you're going to need to know another reaction before we can move on, and that's in the next part. So I would say let's put a hold on this for right now, and let's come back to it after we cover some more, and then you'll be using this concept of reduction along with these problems here. And just one more thing to add, sometimes you want to have a derivative stop at the aldehyde, and so I forgot to mention that if you wanted it to stop at the aldehyde, sort of like the way PCC does for oxidation, if you want it to stop here, you'd use something that can only deliver one equivalent of hydride. And excuse me for my pencil here, it's not working. We would use something called dibol H, which you also sometimes see as a modified hydride reagent. I'm sorry, this is not working. DIBAL, dibol H. Okay, so I would put it as dibol H, or in the book you often see it as lithium with, instead of aluminum with 4 hydrides, you have aluminum with these 3 ester groups, these 3 OR groups, and then an H. Okay, so that delivers one equivalent of H here, and then leaves you at your aldehyde. All right, so that is something that you might see in these problems as well. So we'll come back to that, and next time we'll cover this.